Okay, so first thing I'm asking everybody to do for the quiz, construct a basic exponential shape in a rectangle with no scale. Okay. Originally, I used the word sketch here. I should have used the word construct. But if you want to be reasonably accurate with your graph, you're going to do the whole construction, and I'm not going to explain the construction. Everybody should be able to construct all these toolkit shapes as quickly as I'm doing it. Okay, takes less than 30 seconds. There we have it now. This shape represents a growing plant. It's a fairly rapidly growing plant. It doubles in weight every 5 days. Its original weight is original weight is 10 grams. And what's the weight going to be after 8 days? Can you use your graph to estimate this? You might or might not be able to do that. I'll let you think about it for a minute. Okay, well, how long does it take this graph to double? Like if you're here, where are you going to be when it doubles? Well, it's going to be on this line, because every one of these lines is twice as high as the one before it, right? The y value doubles for every one of these lines. Okay. So in the first place, these are doublings. Okay, from here to here, from here to here, from here to here, and from here to here. Every point on this graph has double the y coordinate of the one before it, because when you construct this graph, every line is twice as close as the one before it to the lower edge of the rectangle, right? So this construction gives us doubling time. Doubling time is from here to here, from here to here, from here to here, from here to here. As we go from this x coordinate to this x coordinate, y goes double its value, right? Didn't say that very well. Y doubles its value. To go from here to here, y goes from here to here, so it doubles. As we go from here to here, y goes from here to here, so it doubles. As we go from here to here, y goes from here to here, so again it doubles. And if we go from here to here, y goes from this to this, doubles again. Okay. So we know that each of these distances for this model has to be 5 days. So if we extend these lines a little bit, having trouble writing days that little on the board, but it says 5 days. And I'm just going to write 5. I don't know, but I'm going to write it out, but you won't be able to read it. That thing after the 5 just says days, okay? Try to write the 5 legibly. Okay. So that takes care of the fact that it doubles every 5 days. Now, we don't know what to let x equal for each of these, but you say the original weight is 10 grams, then, well, you could choose any one of these lines to stand for y equals 10 grams, couldn't you? Up to you. Okay, this is the first, second, third, fourth, fifth line. Show me the figures. Which line do you want to let be the original time? Okay. Now, a couple of people chose the first line. One person chose the second line. And I'm going to use the second line just to take the obvious choice away, but you could have used the first line. It's going to be a little easier to see, though, if you start a little higher. But the first line would have been just fine. But right now, I'm going to choose the second line. So this is going to be day 0. I'm going to use t instead of x. But I'm going to choose to start the time right here. Now, if t equals 0 on this line, label the rest of them. What's t on each of the rest of the lines? Okay, well, we have t equals 0 here, and we have 5-day increments. So between this line and this line, it's got to be 5 days. If t is 0 here, it better be 5 here. Otherwise, it won't be 5 days between. And then clearly then t equals 10 here, t equals 15 here, and t equals -5 here. Okay. Now what's y? Well, we chose to let t equal 0 here, so this would be our initial time when the weight is 10 grams. Okay. So leave myself a lot of room there, but I think it's safe to say y equals 10 on this point, right? Because this represents 0 days, 10 grams. Okay. So what are the rest of these? Label the rest of these lines. Okay, well, this is fairly straightforward. Everybody pretty much got it. One little arithmetic to it. If y is 10 at this point, then it's going to be 20 here, 40 here, and 80 here, because every one of these lines is twice as far from the t equals 0, or the y equals 0. Okay. And then, of course, we could label the lowest line and make sure we got them all. And that would have to be y equals 5. This y equals 10, then y is close to the x-axis, gives us y equals 5. Okay. Now, based on your graph, show me your best estimate of when the weight is, what the weight is after 8 days. Okay. So to estimate when the weight is 8 days, the weight at 8 days, Well, here's t equals 5, here's t equals 10. T equals 8 is going to be a little closer to 10 than it is to 5. So I'm going to say it's maybe here. So now I'm going to draw a vertical line to correspond 8 days, and I'm going to label that line so that anybody that looks at it knows what I'm doing here. Knows how this is going to correspond to the question. And then we find the point where this line crosses the graph. And we sketch this line and we say y equals, well, if it's 20 here and 40 here, it looks like it's a little closer to 40 than it is to 20. Halfway between 20 and 40 would be 30. Let's just say y equals 33. It actually looks maybe a little less than that. I'm going to say 33 because somebody else used the estimate I would have made. Okay. I don't want them to get a big head, even though they're probably going to be more accurate than I am. Okay. And if you estimated 30, that's okay, except, well, there's really nothing wrong with 30. I think it's like 31 or 32. But I don't have a whole lot of confidence in that. Okay, now, when is the weight 50 grams? Then you're going to want to find y equals 50, because the weight is your y value. Okay. So if 80 is here and 40 is here, halfway between is 60, that would be here. Then halfway between 60 and 40 would be about here. So I'm going to say this is where y equals 50. So got to learn to leave myself more room when I'm doing this. Try again. Okay, probably read that. Okay, y equals 50, well, that would be here. So we draw the x projection, or the t projection in this case. What's t equal? Well, here's 10 and here's 15. To the nearest whole number, t would be about 12. Okay, so estimate y equals 33 when x equals 8. Y equals 50 when x equals 12. Okay. Now let's find the function. What's the function here? Well, we have a constant doubling time. Implies we have an exponential function. So we're going to use y equals ab to the t. Y equals 5 when t equals 0. Y equals 10 when t equals 5. Now we could use any of these construction points. Instead of the t equals 0 and the t equals 5, we could have used the t equals -5 and the t equals 15 points. Then we'd say y equals 5 when t equals -5, y equals 80 when t equals 15. Okay? That would work just as well. If you have the coordinates of these points correct, any two will do the job. Okay? Well, we plug in t equals 0 and y equals 5, we get 5 equals ab to the 0, and we get 10 equals ab to the 5th. It's two simultaneous equations. We can easily solve them. We've been over that. Okay. So generally I say solve the first equation for A, plug that into the second equation, and solve for B. Well, A equals 5 from the first equation, B to the 0 is 1, so A equals 5. So we get that immediately. We don't have any power of B to worry about since we know the value of y when t equals 0. So from the second equation, 10 equals 5b to the 5th. B to the 5th equals 2, so b is 2 to the 1/5. And I don't know what the 1/5 power of 2 is. I know that the 1/4 power is around 1.2. So I'm going to guess, let's see, if we use 1.17, then we get about 1.36. For that, I think it's up short of 2. Well, let's just say well, I want to use a precise number. So you've got your calculators, right? Calculate 2 to the 1/5. I'm guessing around 1.15 to 1.17. That's a kind of difficult one to estimate in my head this time of day. Well, I'm sure I'm mobile and on screen. I said first 1.15 to 1.17. And I say that's probably close to 1.17. Well, it's a little less than 1.15. That's approximately equal to 1.14. Now, does it round off to 8 or 9? I think it was 1.48 something, right? Does it round off to 9 or 8? Just thumb up if it rounds off to 9, thumb down if it rounds off to 8. Okay, that's what I was thinking. I thought I saw a couple of 8s there, as a matter of fact, but I don't trust my memory. Okay, so B is this. All right, well, now we've got our model. It's, oh heck, you know what I did? I said y equals 5 when t equals 0 and y equals 10 when t equals 5, right? I was wrong. Although we would have gotten the same thing using those. It's 10 and 20, isn't it? That ought to be 20 and that ought to be 10. Okay, so y equals 10 when t equals 0 and y equals 20 when t equals 5. So my numbers here should have been 10 and 20. Now, putting the right numbers in here. Instead of 10, 5, it's 20 and 10. Either way, it still divides out to give us 2. It makes no difference in the solution, but what I had there was incorrect. If I'd have used 5 and 10, I would have had to use b to the -1 here, or b to the -5 and b to the 0. Okay, you don't need to understand that. Just write it down correctly. That's the way it'll look. So we're using points 0, 10 and 10, 20. We get b approximately 1.149. And of course, we get a equals 10. So model is ten times 1.149 to the t. So now answer these two questions again, not using the graph, but using the equation. Okay, I don't think anybody had any trouble getting the weight after 8 days. I haven't checked to see if anybody got the time when the weight was 50 grams. But everybody just kind of went ahead. I wrote this down, but I don't think anybody even looked at it. Just punch it in your calculator. They should have written down t equals 8, so y equals 10 times this, because there's the logic of how you're breaking it down. Just don't write down an equation, start punching buttons. Write out what you're doing. It only takes about 3 extra seconds to write y equals 8, so. If you write fast, less than that, okay? Or write something equivalent that kind of reads logically, okay? It shows the flow of your thinking. And that's for your sake, not mine, okay? If you write down just enough that I see that you knew to evaluate the function at t equals 8 on a test, I'd accept it. But what you're not doing, if you don't write down these things, is you're not reinforcing it, so you're going to be more, so that you would be more likely to get it right on the test, okay? So what do you write for the question, when is the weight 50 grams? Well, first you identify y equals 50. So then what? And you could write something, you say, since y equals 50, then, but y equals 50, so is short, okay? Use your own decision, what you want to write, how you want to write it, but write something that connects this to a function. Okay, now everybody is now made a connection, very good. Since y equals 50, you've got the equation, so you get 50 equals 10 times 1.149 the t. We just replaced y by the 50. Everybody did that. And now what kind of an equation is that? How do you solve it? Well, a lot of people have, well, what kind of equation is that and how do you solve it? All right, well, first thing I do with this equation, let's go ahead and write it up here so we have room to work on it. This is an exponential equation. T is in the exponent. So we change it to the logarithmic form. Okay. Let me write down what we know that b to the t equals, or b to the x equals b to the a equals c, I think those are the letters I use, is equivalent to log base b of c equals a. Now, if you're solving these equations without writing this down every time, you probably don't remember it. Okay. So again, if you write out what you're doing at every step, you're going to reinforce it, and it doesn't take long to write it out. It might seem tedious because you probably got it sitting there in front of you. Put that thing away. Write it from memory. If you don't remember, then take a peek and remember it the next time. Does that make sense? This is how you do your homework. You don't do your homework with everything you need in front of you because you need to prepare for passing a test when you don't have any of that in front of you. That might give you a few little hints, but I'm not going to tell you what they are. Okay? I'm not going to write that out for you. Okay, so t in the exponent changed to log form. Now, this is not in either of these forms. You want it in the form b to the a equals c. So you want that 1.149 to the t to be by itself on one side of the equation. Well, get it nice and clean. We get 1.149 to the t equals 5. So now, changing it to logarithmic form, we get t equals log base 1.149 of 5. Okay, yeah, you can plug that into your calculator. That could be log 5 over log of 1.149. And now you got something you can plug into your calculator. I want to see this step. Okay, because there's an important property of the logarithmic function. Basically, that this function is vertical stretch of this one, and what you get when you divide it is the vertical stretch factor. Okay, might not be important on this problem, but it could be important on another one, so I want to see that breakdown. Okay, well, when you do that, I think you get something about 11.6. I think I saw 11.57. Okay. Now, how does that compare with the estimate I made from my graph? Well, the estimate was fairly easy to the nearest whole number was 12, right? So that my estimates on this graph are pretty well confirmed by the more accurate results that we get, the 4 significant figures from the model. Okay? And since this is a growing plant, we don't think that we can estimate it down to 4 decimal places when the thing is going to actually reach 50 grams. Okay? 11.6 is probably better. 12 or 11 is probably a good estimate. Figure on the 11th or 12th day, somewhere around there. Okay? And our graph gives us results. Unless our plant is somehow engineered, being grown under predictable conditions, but there are genetic variations between any 2 plants. Okay? Maybe it's a clone of another plant. Then we would expect to be able to estimate it a little more accurately than we could from the graph, but it's just plant growing. You want to know about when. We know that this plant tends to double every 5 days under good conditions. And we can make a prediction from the graph. We don't even have to go to the function. But many times you have to go to the function. Okay? If you draw a good graph, then you have to do a lot of algebra. If you're in a hurry to get your result and you want to get a bunch of them, construct a bunch of good graphs. It's quicker than doing all the algebra. Okay? Of course, if you're at your computer, you go under Wolfram Alpha or Desmos or whatever and get an answer real quickly. But if you're trying to think it through, this is really good thinking tool. And this is a really good analytical tool. That all makes sense? Okay, now I want you to estimate from your graph I don't want to use something that I've already used. For these four values of t, use your graph to estimate the y values and put them in a table. Your table is just going to be y versus t. Make your own estimates. Okay, except for the t equals 17 value, people's estimates are very close to one another's. And kind of taking typical estimates, 13, 28, 60, 110. Now, don't know where this is going yet, but it's kind of neat. I'm going to calculate the natural log of y values. Okay, got a natural log key, a button, or whatever you can use in your calculator. So you ought to be able to pretty quickly get these values. Okay, now I've asked everybody to take these estimates from the graph. Okay, those are just kind of my estimates. And make a table of y versus t. Now we're going to calculate natural log of y for each of these. And I made estimates that were kind of close, but that was pretty far off, of what these values ought to be. Had to change most of them by a little bit. But I trust the accuracy of your calculators more than I trust my ability to figure out powers of E in my head. So we get 2.6, 3.2, 4.1, 4.7. Okay. Now what I want you to do is I want you to make a graph and make your axes a little more perpendicular than I made mine. If you use the line y equals 16, then it's going to come close to spanning our t values, right? And if we use a graph that goes out to x equals 4, we leave ourselves a little bit more room. Then we can kind of estimate where x equals 2 is and x equals 1, x equals 3, and all that. In other words, we can scale the graph based on these two lines, right? So scale your graph and plot these points. Okay, now I'm going to go ahead and do this. Some of you are pretty far along. We have 4 points. Some are still scaling the graph. So let's talk about scaling the graph. Why did I use 16? Because these values go up to 17. Okay. I like 16 because I can divide it in half and a bunch of times. Okay, 16 is a power of 2. I like powers of 2. I use 4 here because, well, things go up to almost 5. If I know where 4 is, I can figure out pretty well where 5 is. So having 16 here and 4 here, well, I just cut this rectangle in half and I've got x equals 2. Cut in half here, and that gives me x equals 1. I cut this part of the rectangle in half, and it's not all that accurate. she was, my line wasn't all that straight. I wasn't all that vertical. Okay, but see, I've got a scale now. And if I want x equals 5, I just go over about that far. Now I've got x equals 5, right? Okay. Now on my, oh heck. If you did what I did, it's okay. You're still going to get a straight line, but my 16 should have gone here. My 4 should have gone here. So that's going to be 2. That's going to be 1. I haven't written y equals 4 here because really it's natural log of y, isn't it? So natural log of y is 4. Natural log of y is 2. Natural log of y equals 1. And this line got kind of down in the middle. Okay. Over here, I have t equals 16. If I cut this in half, I get t equals 8. Cut this in half, I get t equals 4. Cut this in half, I get t equals 12. And now to plot my points, 2, 2.6. Well, okay, t equals 2 here. And 2.6, well, here's 1 and 2, here's 4. Halfway between 2 and 4 is 3. That would be the natural log of y is 3. So 2.6 is maybe about here. Now, I don't want to make too many horizontal dotted lines or they'll get confused, but this is between natural log of y equals 2 and 3, here to here. 2.6 is a little more than halfway between 2 and 3, so that's reasonable. Okay. Now, when t equals 7, well, that would be about here. This is 4 and this is 8. T equals 7 is about here. And we get 3.2. So that's going to be about here. T equals 13. Well, that's just a little bit to the right of 12. We're going to get 4.1. Well, if that's 4, 4.1 is a little more than 4. And then when we get out to 17, well, t equals 17 will be a unit to the right of t equals 16. And we're going to get 4.7. Well, I could make another line here. The natural log of y equals 5. And that's going to be here. What do you notice about those points? Well, first thing you look at when you got a bunch of points is you hope the line is a straight line because that makes things really easy. Okay, well, this straight line for these points probably, I don't know where the chalk is going to choose to make a mark, but okay. There's a straight line that does a pretty good job of fitting the points. I say try to come as close as possible to all the points on the average. Okay. So we want it to kind of go between the points and minimize the average distance between the points. Now, if you study statistics, you see that what you really want to do is find the line that gives you the smallest average squared distance. And there's a subtle difference there that I don't expect you to be able to visualize, at least at this point, okay? But there's the line. And what's the equation of that line? Figure out the equation of that line for me. All I gotta do is the slope and the y-intercept. Okay, I'm not sure how much of that I recorded, but we construct a graph. I use the line t equals 16 here. Here's my t-axis. And this axis, the vertical axis, is actually going to be natural log of y. And then, since the natural log goes up to about 4.7, I use the line t equals natural log of y equals 4. Cut that in half, I get natural log of y equals 2. Halfway, again, I get natural log of y equals 1. Then halfway between 2 and 4 is 3. And I plot my points. They turn out to be pretty close to a straight line. So I sketch the straight line. And now I ask, I have a comment, the straight line fits the points well. What are our estimates? What's the slope? What's the y-intercept? Okay. So let me just see what you got. Y-intercept is right here. Now from where you're sitting, it looks pretty close to 2, but it's a little above 2. So I'm going to say the y-intercept is about 2.1. Now the slope, well, I can draw a fundamental triangle from here to here. And it looks like the rise is about 1 up to here, 2 up to here, and then about 6.6 more. And the run, well, the run is 17. So the slope is 2.6 over 17. And which is about 0.16. So my line natural log of y is 0.16 plus 2.1, right? So solve for y. Okay, now we're short on time, so I'm going to finish the solution for you. Very simple. We just use b to the a equals c, log base bc equals a, and we get y equals e raised to the 0.16t plus 2.1. Okay, so y equals then e to the 0.16t times e to the 2.1. E to the 0.16t is pretty close to 0.17. So our e to the 2.1 is approximately equal to 7 times e to the 16th raised to the tenth power. I'm just using laws of exponents here. E to the a plus b is e to the a times e to the b. E to the a to the b is e to the a times b. So it's about 7 times 0.17 to the t. Now, the model we got was 10 times 1.149 to the t. Okay? In other words, the function that we used for all of this was this function I get when I do all this stuff, come back around from estimates on the graph, isn't all that close, but it's not all that far away, right? So if I made a slight error in estimating the slope of my graph, or in estimating points from my graph, it's not going to work out that well. Okay, this is an estimate of the function that fits the table, wherever the table went. Okay. So we made estimates from the table. From that, we made an estimate of the function. And it came out reasonably close. Now, what you're going to do for homework is logarithmic model. Okay. If you make a good effort on the homework, then I might well extend it a couple of days. Okay. Because there's some stuff your book does that doesn't look anything like this. Okay. But this is really what's going on. And this is actually, you know, your book talks about semi-log paper. You would use that in a science class. But for a lot of applications, you're not going to be carrying semi-log paper around with you. Okay. Unless you know you're going to need it. And you can still make sketches and make estimates and understand much more about what's going on with the semi-log paper and the models you get. So we'll talk more about that next time. Everybody's listening. Okay. The suggestion I make for next time, we're going to be talking about simultaneous equations. Review what you did in chapter 2 on solving 2 equations for 2 unknowns. Okay. And of course, you're in the MDE 61. We've already done that. You're familiar with it. Not that difficult. It'd be good if you were familiar with it when you came in.